Good morning friends, welcome to Turbo Machine classes. I am Professor V. Sushant Kumar, Department of Mechanical Engineering, Angadi Institute of Technology and Management, Belagavi. In today's class, we will discuss about static and stagnation properties. Before proceeding to the concepts of a turbo machine, it is very important to understand what is static and stagnation properties. Okay. When a fluid is at rest, one can define various thermodynamic properties like pressure, temperature, volume, etc., which are directly measurable. But these properties are different when the fluid is flowing and hence depend on the speed of the flow and the condition under which measurement is being made. Dealing with the turbo machines, fluid can be compressible and flowing at very high speed, exceeding the speed of sound, and fluids can be incompressible where velocities are relatively low and kinetic and potential energies of fluid are often large and constitute major fractions of the total energy available for conversion into work. Neglecting kinetic and potential energy, they cannot provide sufficiently accurate results for design purpose. It is therefore necessary to formulate equations based on the actual state of fluid, including all the energies at the given point in the flow. Taking these factors into account, we use equation of thermodynamics to specify two fluid states. They are called as static and stagnation states. Now let us understand what is static state. If the measuring instrument is static with respect to the fluid, here static refers to the measuring instrument, the relative motion between the measuring instrument and fluid particle is zero, means there is no relative motion between the measuring instrument and the fluid particle. Then the measured quantity is known as static property. This static property, it can be anything. It can be pressure, velocity, temperature, enthalpy. Okay. The state of particle fixed by a set of static properties, we call it as static state. Now let us understand this term with an example. Consider a fluid flowing at a high speed through a duct. In order to measure the properties of the fluid, one may insert an instrument such as pressure gauge or thermometer at some point in the flow. Now, we can measure the properties in two ways. The first one is measuring instrument moves at the same local speed as that of the fluid particle. So what it means is the measuring instrument, there is no relative motion between the measuring instrument and the fluid particle. Means you can just imagine the measuring instrument, when you insert into the duct, it is moving at the same speed as the fluid particle. You are literally moving the measuring instrument, okay, along with the fluid particle, means to make sure that there is no relative motion between the fluid particle and the measuring instrument. The second method is measuring instrument is stationary with respect to the fluid particle. So you are just inserting the instrument into the duct and holding it there. That is the second method. First type of measurement is said to determine static properties of the fluid. If you go by first method, means if you make sure that the measuring there is no relative motion between the measuring instrument and the fluid particle, then that property we call it as static property. That is how you measure. But practically it's not possible, right? You cannot move the measuring instrument along the speed of the fluid particle. In the previous slide, we understood what is static state. So if you want to measure the static properties, then there should be no relative motion between the measuring instrument and the fluid particle. So that can be done by two ways. One, moving the measuring instrument along the speed of fluid particle, that is one method. And second one, you are just maintaining, if you are inserting the measuring instrument into the duct, you are not inserting deep into the duct. Okay, the measuring instrument surface and the surface of the duct coincide. Okay, so I'll discuss that in the next slide, wherein I'll explain you with the sketch. Now let us understand the definition of stagnation state. So definition goes like this, that stagnation state is defined as the terminal state of a fictitious isentropic work free and steady flow process, during which the macroscopic kinetic and potential energies of the fluid particle are reduced to zero. Means when the fluid is flowing, if you make its kinetic and potential energy equal to zero, means you are converting that into some other form. Okay, so the condition is, we are considering fictitious imaginary fluid, isentropic, okay, and work free and steady flow. These are the conditions. Okay, then the properties that are measured in this condition, we call them as stagnation properties, and all those properties we describe the condition at that instant, we call them as stagnation state. Stagnation state specified above is not representative of any true state of the fluid. No real process leads to stagnation state, because no real process is truly isentropic and perfectly free from thermal exchange with the surroundings. It is not possible to have a perfect stagnation state, because no fluid is isentropic. Okay, and it's perfectly free from thermal exchange with surroundings. But despite the impossibility of achieving, if proper care is taken to account for errors in measurement and appropriate corrections is incorporated, many of the properties measured with the instruments like pitot tube, thermocouples do provide readings that approximate stagnation properties closely. So we'll understand more, okay, with the help of the sketch. So we have studied what is static state and what is stagnation state, what is static property, stagnation property. Let us try to understand those terms with the help of the sketch. Here we have a duct. This is a duct. Okay, inside duct some fluid is flowing with a velocity v. So if you look, there are two instruments which are inserted into the duct. So one is a piezometer, which measures the pressure, and one more is pitot tube, which also measures the pressure. But if you look here, the position of these two measuring instruments, pressure measuring instruments, is different. If you look at the piezometer opening is just coinciding with the piezometer opening is just coinciding with the surface of the duct. Okay, and a pitot tube pitot tube is deep into the duct. Okay, so now this piezometer, which is a pressure measuring instrument, its surface coincides with the opening is coinciding with the surface of the duct. So here what happens, we have studied in our lower semester, at the boundaries, at the surface, we have no slip condition. No slip condition means the velocity of fluid particle is 0. Okay, so when I insert my measuring instrument in such a way that its surface coincides with the surface of the duct, then here I will have the fluid with 0 velocity. So we can attain our static state definition. So what the static state definition states, there should be no relative motion between the measuring instrument and the fluid particle. So here at the surface, there is no relative motion between the fluid particle and the instruments. So that's why this piezometer is positioned in such a way that its opening and surface of the duct coincides, so that we get 0 velocity. Whereas the pitot tube is inserted deep into the duct. If you look from the sketch, it is inserted deep into the duct. So when the fluid, when it comes with some velocity, its kinetic energy will become 0 at the entrance. Okay, because already some fluid is present in this tube. Okay, so suppose let us consider, for example, there is one water particle or fluid particle which tries to enter here, and its kinetic energy becomes 0. So when its kinetic energy becomes 0, so that energy has to be converted into some other form, right? So it is converted into pressure energy. So that's why if you observe the level, the fluid level in both the measuring instruments, in piezometer this is the fluid level, whereas in pitot tube this is the fluid level, because the piezometer measures the static pressure, whereas pitot tube, which is inserted in this fashion into the duct, it measures stagnation pressure, means the kinetic energy is brought to 0. Okay, and that kinetic energy has converted into pressure. So that's why there is a difference, and this difference of height we call it as dynamic pressure. Okay, so stagnation pressure is sum of static pressure plus dynamic pressure. I hope the concept of static state and the stagnation state is clear. I'll repeat once again. If you want to measure the static properties, the relative motion between the fluid particle and the measuring instrument should be 0. That's why we have, for example, if you take to measure the pressure, that's why we have inserted this piezometer here in such a way that here we have no slip condition, so there is no relative motion between the fluid particle and measuring instrument. If you want to measure the stagnation pressure, then we are going to insert the pressure measuring instrument deep into the duct, so that the kinetic energy of the fluid is brought to 0, and that energy is converted into a pressure energy. Okay, so that's why the level indication, fluid level in the pitot tube, okay, is greater than the fluid level in the static pressuring instrument, that is piezometer. Okay, so if you go by this method, then we are going to measure stagnation pressure. If you go by this method, if you place your instrument in this fashion, we will get static pressure means static properties. The difference of these two is called as dynamic properties. So here stagnation property formula is written here. Stagnation property is static property plus we have got some expression rho into v square by 2g. So in the following slides we will see how we got this expression, how to write the stagnation properties in terms of static properties. Between static and stagnation properties. So we can express stagnation properties in terms of static properties, and we'll see the expression of that. So we get this relation by the first law of thermodynamics. Let us consider a steady flow process. Okay, from the first law of thermodynamics, we get this equation. Okay, so heat transfer and work transfer, the difference of energy transfer, okay, will give us delta H plus delta Ke delta P. So what is Q here? It is energy transfer as heat per unit mass, and W is energy transfer as work per unit mass, and here H is static enthalpy, Ke refers to the kinetic energy, okay, v square by 2 of the fluid particle velocity, and P refers to potential energy, that is Gz. Okay, we are considering this equation per unit mass, okay, where Z is the height of the particle above the datum at the point under the consideration. We have studied that the static state is the initial state, okay, in a fictitious isentropic work free steady flow process, and stagnation state is the terminal state, okay, where both kinetic and potential energies are zero. Okay, the difference in enthalpies between the stagnation and static state is obtained, okay, by equating QW is equal to 0. Means we get this Q equal to 0, W equal to 0 from the definition. Okay, steady flow process, okay, and isentropic process. Okay, if you just go through the stagnation properties definition, okay, so Q is equal to 0, W is equal to 0. Okay, so and in the stagnation state kinetic and potential energy will be 0. Okay, and only remaining will be delta H. What is delta H? It is difference of stagnation enthalpy minus static enthalpy. So here suffix 0 refers to stagnation state and suffix I refers to static state. Now we can write this equation, okay, this Q minus W is equal to delta H, delta Ke, delta P, this equation which we got from first law of thermodynamics, it can be written as, okay, we separate this, okay, for stagnation state and static state. So H plus Ke plus P, so this expression is for stagnation state, okay, and minus H plus Ke plus P, this is for static state. Okay, so we have just, instead of delta H, okay, delta Ke, delta P, I have written the above expression in terms of stagnation properties minus the static properties. Okay, and we know that Q and W, heat transfer and work transfer, is equal to 0, and kinetic energy in stagnation state is 0 and potential energy in stagnation state is 0. So if you cancel out, so Q is equal to 0, W is equal to 0, and the kinetic energy in stagnation state is 0, potential energy in stagnation state is 0. So what remains is H naught minus H plus K plus P for static state. So that expression is written here. Okay, H naught is equal to, okay, static enthalpy, static kinetic energy, static potential energy. So usually we drop this suffix I, okay, the static properties, and we can write the expression as H naught is equal to H plus Ke plus P. So from now onwards, wherever we write H, it means that it is static enthalpy until and unless if suffix 0 is written. Okay, if H naught is written, then it means that it is stagnation property. Okay. We know that a process changing from static to stagnation be isentropic. What is isentropic? Isentropic means entropy remains a constant, that is S naught is equal to Si, and hence entropy in stagnation state is equal to entropy in static state. Thus, two independent stagnation properties, namely enthalpy H naught and entropy S naught, have been determined in terms of known properties at the static state. Okay, so here we are going to find the expression for static enthalpy and stagnation enthalpy and stagnation entropy. Okay, so according to state postulate, okay, this word state postulate we have studied in basic thermodynamics. Okay, the knowledge of any two independent properties at a specified state is sufficient to fix the state of the simple compressible substance. Means if you want to fix any state, we need at least two independent properties, okay, to fix the state of a system. Okay, the stagnation state is totally determined, and it should be possible to determine any other required property of stagnation state in terms of known properties H naught and S naught. Okay, so from the second law of thermodynamics, okay, we have this expression T ds is equal to dH minus V dP. So here T refers to temperature in Kelvin, ds refers to change in enthalpy, and dH refers to change in enthalpy, and V refers to specific volume, and dP refers to change in pressure. Okay, since entropy remains constant, changing from static to stagnation, so this ds is equal to 0, means this whole expression is equal to 0. So what remains is dH minus V dP. That's what that is written here, dH is equal to V dP. Okay, so now integrating this equation, okay, we get the difference between stagnation and static enthalpy. Okay, so now if you want to find the integration of dH, okay, we need to know the relation between specific volume and dP, change in pressure. Okay, if we know the relation between this V and dP, then we can find the expression of H naught minus H. Okay, so to find the relation between V and dP, we are considering two cases. One is for the incompressible fluid, and second one is for the perfect gas. Now let's see for incompressible fluid the expression. So before going to details in this slide, I would like to tell you the relation between density and specific volume. So density is nothing but mass by volume. The unit of density is kg per meter cube. The inverse of density, okay, inverse of density is nothing but specific volume. Okay, specific volume unit is what? Meter cube per kg. Okay, just inverse of density. Okay, now for an incompressible fluid, okay, incompressible means no change in volume, negligible change in volume. Okay, change in volume dV is equal to 0. Okay, so this dV is nothing but inverse of density, where rho, this symbol rho refers to density of the fluid. Rho is density of the fluid. Okay, so since density is constant and independent of the state, okay, so let us consider this equation. In the previous slide we got this equation, okay, from the second law of thermodynamics, second TDS equation. that is integration of dH is equal to integration of V into dP. Okay, so integration of dH is nothing but H naught minus H. Here H naught is stagnation enthalpy and H is static enthalpy. So actually we are supposed to write HI, since I told you before. Okay, usually for static state we drop this suffix I. Okay, so if H is written, it is static enthalpy. Okay, so now let's coming down to the equation. Okay, so here V is specific volume. Okay, it is inverse of density. Okay, so for an incompressible fluid V is constant, so V will come out of integration, that is 1 by rho. Then what remains is integration of dP. Okay, so what is the integration of dP? It is nothing but P naught minus Pi, means integration from static to stagnation state. Okay, so P naught minus Pi. Okay, and divided by rho, that is inverse of 1 by rho. 1 by rho is nothing but specific volume. Okay, now we got this equation after the integration, means considering for incompressible flow. Okay, H naught minus H is equal to P naught minus P by rho. Okay, and previously we have derived equation for we have derived this expression H naught is equal to H plus Ke plus P. Stagnation enthalpy is equal to sum of static enthalpy plus kinetic energy plus the potential energy. Okay, so if I take this H on the left hand side, we get this equation H naught minus H is equal to sum of kinetic energy and potential energy. Okay, so we know what is H naught minus H. H naught minus H is nothing but P naught minus P by rho. That's what we are substituted. Instead of H naught minus H, P naught minus P by rho is substituted, and on the right hand side, okay, we have written the expression for kinetic energy, that is V square by 2, and expression for the potential energy, that is Gz. Okay, so now if you divide this row separately and rearrange the terms, we get it as P naught by rho. Okay, is equal to this P by rho will come to the right hand side. Okay, P by rho plus V square by 2 plus Gz. Okay, so on the left hand side we have stagnation pressure, and on the right hand side we have static pressure plus kinetic energy plus potential energy. Okay, the stagnation pressure of the incompressible fluid has now been expressed in terms of its static pressure, velocity and height above the specified data. Okay, so we have expressed stagnation pressure, okay, in terms of the static pressure and kinetic energy and potential energy. According to first law of thermodynamics, the stagnation enthalpy H naught and stagnation pressure P naught should be constant along any streamline which experiences no energy transfer as heat or as work. Hence, for an incompressible frictionless fluid in steady flow, it is seen that stagnation pressure remains constant along a streamline in an unaccelerated coordinate system. So this is Bernoulli's theorem, okay, which we have studied in our fluid mechanics subject. Okay, next let us consider again the second law of thermodynamics. From the second law of thermodynamics we get this equation. Okay, this we call it as first TdS equation. Okay, T temperature in Kelvin, ds change in entropy is equal to du, okay, change in internal energy, and P refers to pressure, dV refers to change in volume. Okay, so for a system from static to stagnation state, okay, change from static to stagnation state for an incompressible fluid. Okay, uh, entropy is zero. Okay, there is no change in entropy, and work is also zero. Okay, so entropy is zero and pdv work is also zero. What remains is du is equal to 0. It means that u is equal to u naught, that is the internal energy. Very important statement. The internal energy of an incompressible fluid in the static and stagnation states are equal. It means that the internal energy of the fluid in static state is equal to the internal energy of the fluid in stagnation state. Since internal energy of an incompressible fluid is a function of temperature alone, okay, internal energy is function of temperature alone. Okay, means as temperature varies, the internal energy varies. Okay, we can conclude that u naught minus u is equal to c t naught minus t is equal to 0. What it means? Okay, so it means that t naught is equal to t. Temperature in stagnation state is equal to temperature in static state. Okay, the local static and stagnation temperatures are equal to each other at every point in incompressible and loss free fluid flow. Okay, so I'll just summarize what we discussed in this slide. Okay, so we have seen that the internal energy in static and stagnation states are equal, and the temperature in stagnation state and static states are equal, as the internal energy is function of temperature. So now let us consider the second case, that is for a perfect gas. Okay, we will see the relation between the static properties and stagnation properties. Okay, we know that enthalpy is function of temperature alone. Okay, so we know this equation, or in previous slides we derived this. H naught is equal to H plus Ka plus P, that is stagnation enthalpy is equal to sum of static enthalpy plus kinetic energy plus potential energy. And since enthalpy is function of temperature alone, okay, we can write this H naught, okay, as Cp T naught, where this C refers to specific heat. Okay, Cp refers to specific heat at a constant pressure. Okay, H naught is equal to Cp into T naught is equal to H static enthalpy. I can write it as Cp into T, that is specific heat at constant pressure into temperature, plus kinetic energy we have written it as V square by 2, and potential energy Gz, means it is, we are writing all this equation per unit mass flow. Okay, so when I take this Cp on the right hand side, okay, what remains on the left hand side is T naught, that is stagnation temperature. Okay, Cp by T by Cp get cancels, what remains is T, and V square by 2 plus Gz divided by Cp. Okay, so now we have expressed stagnation temperature in terms of static temperature and plus kinetic and potential energy. So this equation will give us the relation between stagnation temperature and static temperature. Okay, so now let us try to simplify this by substituting the values, whatever values we assume. Okay, so in an compressible flow machines, okay, so usually the fluid velocity varies between 60 meters per second to 600 meters per second. This is the range. Okay, this is the range of the fluid velocity in a compressible flow machine. Okay, remember, in a compressible flow machine the velocity varies between 60 to 600 meters per second, and usually the datum height, okay, it rarely exceeds 4 meters. Okay, in most steam and gas turbines. Okay, it doesn't exceed beyond 4 meters. At the max it can be in and around 4 meters. Okay, now let us considering the minimum values of velocity and z. Okay, so kinetic energy I am substituting the minimum flow velocity, that is 60 meters per second. Okay, so we get 1800 joules per kg. Okay, and considering minimum datum height, we get 39.24, okay, joules per kg. Okay, so from the above values we observe that magnitude of kinetic energy, okay, far in excess of the potential energy. If you check the values of the kinetic energy and potential energy, kinetic energy value is far exceeding than the potential energy in most compressible flow machines. Okay, so it is therefore usual to neglect the term gz, okay, in comparison to the term v square by 2. Okay, so what I mean to say is, okay, since the kinetic energy is far greater than the potential energy, we neglect gz, then the above expression, okay, can be written as T naught is equal to T plus V square by 2 Cp. Okay, we have just simplified the expression making some assumptions. So now let us try to substitute the values for Cp, and let us express in terms of Mach number. So we know that specific heat at constant pressure can be written as gamma into gas constant divided by gamma minus 1. So these expressions we have studied this in our basic thermodynamics. Okay, relation between specific heat at constant pressure and specific heat at constant volume. Okay, so expression for this T naught is equal to T plus V square by 2 Cp now can be written as, okay, you substitute instead of Cp, okay, these values. Okay, so we get this expression, okay, and we know what is Mach number. Mach number is velocity of the fluid divided by the speed of the sound. Okay, V by C, where C is speed of the sound in the gas at static temperature. Okay, and this C, velocity of sound, the expression for this is square root of gamma into gas constant into T. Okay, so now substituting all this in the temperature, stagnation temperature, static temperature relation, okay, we get the expression for stagnation temperature in terms of gamma, that is the ratio of specific heats, and Mach number. Okay, so topics discussed in today's class, we discussed about what is static state, and we discussed about what is stagnation state along with the sketch. Okay, we tried to understand what is static pressure and what is stagnation pressure and what is the relation between that. Okay, and the next topic we discussed was relation between static and stagnation state. We considered two cases. The first one is the relation between static and stagnation state for incompressible flow, and the second case was perfect gas. Thank you for watching the video. If you have any doubts, you can kindly contact me. Thank you once again.